Now let's move on. As we discussed before, acids are commercially sold as highly concentrated aqueous solutions. For instance, take sulfuric acid. It is sold as 98% aqueous solution by mass or by weight. That means if you take 100 grams of this solution, 98 grams of it is sulfuric acid and only 2 grams is water. And if you express this concentration in terms of molarity, it will be approximately 18.15. So this is a highly concentrated solution of sulfuric acid. Such highly concentrated solutions are known as stock solutions because we stock these chemicals at this high concentration. But we do not use these solutions in the laboratory at these high concentrations. The concentrations of the solutions that we use in the laboratory are far less than the concentrations of these stock solutions. Now the question is, from where do we get these low concentration solutions that we commonly use in the laboratory? We have to prepare them from these stock solutions. Say for example, we need 100 milliliters of 0.4 molar sulfuric acid solution for a particular chemical reaction. How do I get this solution? We have to prepare it from this stock solution. How do we do that? Let us see. See, obviously what we have to do here is somehow calculate the volume of the stock solution required to prepare the desired solution. Once you figured that out, take that volume of the stock solution and place it in an empty volumetric flask. Here, the volume of the solution we are trying to prepare is 100 milliliters. So you would take a volumetric flask of volume 100 milliliters. Then add solvent or water in case of aqueous solution until the liquid level reaches this mark. Then the volume of the solution is exactly equal to 100 milliliters. This process of adding solvent or water in case of aqueous solution to a stock solution to prepare a solution of lesser concentration is called diluting. So we prepare solutions of lesser concentrations from the stock solutions by diluting them. How do you dilute them? You add solvent or water in case of aqueous solution to a given volume of the stock solution. Now the question is, how do we figure out the volume of the stock solution required to prepare the desired solution? Let us say the volume of the stock solution required is V1 and its molarity is M1. And say we finally wanted to prepare a solution with volume V2 with molarity M2. See here, we are trying to dilute V1 volume of the concentrated stock solution with molarity M1 to V2 volume of the dilute solution with molarity M2. And how are we doing that? By adding solvent or water in case of aqueous solution to a given volume of the stock solution. All we are doing is that and nothing else. And during the diluting process, there are two things that are changing. obviously the volume of the solution is increasing because you are adding more and more solvent to the stock solution, right? Secondly, the concentration of the solution is decreasing. As you add more and more solvent to the stock solution, obviously the concentration of the solution decreases. That is, the amount of solute in a given volume of the solution decreases because we are adding more and more solvent. But there is one thing that is not changing during this process. That is the amount of solute present in the solution, or the number of moles of solute present in the solution. Because during the diluting process, we are only adding solvent to the stock solution. Therefore, the amount of solute must be same before the dilution and after the dilution as well. Now, how do you figure out the amount of solute or the number of moles of solute present in the stock solution that we took? Now, let us say the amount of solute present in the volume of the stock solution that we took is NB1, and the amount of solute present in the dilute solution that we prepared is NB2. Now, what is the expression for molarity? It is the amount of substance of solute over the volume of the solution, of course in liters. Then how do you get NB1? It is the product of the molarity of the solution and the volume of the solution. Similarly, M2 is equal to NB2 over V2, or NB2 is equal to M2 times V2. Now, as we just discussed, during the dilution process, the amount of solute does not change. So, the number of moles of solute must be same before and after dilution. So, NB1 must be equal to NB2, or in other words, M1 times V1 must be equal to M2 times V2. Then what will be V1? It is equal to M2 times V2 over M1. See here, we know the value of M1, that is the concentration of the stock solution. We know the volume of the dilute solution that we are preparing, that is V2, and we also know the molarity of the dilute solution that we are preparing. So we know M1, we know V2, we know M2. By putting those values here, we can calculate on paper the volume of the stock solution required to prepare the desired solution. And this equation M1V1 is equal to M2V2 is called dilution equation. Here V1 is the volume of the stock solution or the concentrated solution. M1 is its molarity. V2 is the volume of the dilute solution that we are preparing, and M2 is the concentration of the dilute solution that we are preparing. Now let us work out a few examples on dilution. Stock solution of sulfuric acid is 18.4 molar. What is the molarity of the solution obtained by diluting 45 ml of the stock solution to 180 ml? This is a straight question. The dilution equation is M1V1 is equal to M2V2. Now the molarity of the stock solution is given as 18.4 mole per liter, and the volume of the stock solution taken is 45 ml or 45 times 10 to the power of minus 3 liters, and the volume of the dilute solution is given as 180 ml or 180 times 10 to the power of minus 3 liters, and we have to calculate the molarity of the dilute solution obtained. Simply substitute these values in this equation to calculate the value of M2. So M2 will be equal to M1 times V1 over V2. M1 is 18.4 mole per liter. V1 is 45 times 10 to the power of minus 3 liters over V2 is 180 times 10 to the power of minus 3 liters. Cancel these two and simplify this to get the value of M2 again in mole per liter. What do we have next? Commercially available concentrated hydrochloric acid, that is stock solution of hydrochloric acid, has a concentration of 12.4 m. What is the volume of concentrated hydrochloric acid required to make 1 liter of 0.2 molar hydrochloric acid solution? Again, a simple straight question on dilution equation, that is M1V1 is equal to M2V2. Here M1, that is the concentration of the stock solution, is given as 12.4. Remember the units, mole per liter. We are asked to find out the volume of the stock solution required. So we need to calculate the value of V1, and we are given M2, that is 0.2, again mole per liter, 0.2 molar, right? And V2 is given as 1 liter. Substitute these values here and simplify it to get the value of V1. Take that as an exercise. Then the next question says, a sample of a stock solution of ammonia that has a concentration of 14.8 m is diluted to 20 times its original volume. Find the concentration of the resulting solution. Again, a straight question on dilution formula, that is M1 V1 is equal to M2 V2. Here M1, that is the concentration of the stock solution, is given as 14.8 m, that is 14.8 mole per liter. Let us say the volume of the stock solution taken is V liters. Then what is the volume of the dilute solution? It is diluted to 20 times its original volume. That is V2 is equal to 20 times V liters. Original volume of the stock solution taken is V liters. So it is diluted to 20 times its original volume. And we have to calculate the concentration of the dilute solution. Substitute these values here and simplify to get the value of M2. Now let us get back to our chemical reactions and stoichiometric calculations. Let us look at this question. It says calculate the volume of 0.120 molar sodium hydroxide required to neutralize 30 milliliters of 0.200 molar sulfuric acid, and here is the balanced chemical equation for that reaction. Obviously, this reaction is taking place between the aqueous solutions of sodium hydroxide and sulfuric acid, not between pure sodium hydroxide and pure sulfuric acid. see whether the reaction takes place between the pure reactants or between their solutions. Because the reactants are the same, they combine in the ratio of their stoichiometric coefficients. That is, 2 moles of sodium hydroxide reacts with 1 mole of sulfuric acid, whether the reaction takes place between the pure reactants or between their aqueous solutions. Now, how do we answer this question? Now, let us break it down. From the stoichiometric coefficients, we understand that 1 mole of sulfuric acid reacts completely, whether pure or in aqueous solution, 2 moles of sodium hydroxide. But for this reaction, how many moles of sulfuric acid did we take? That is not given in the question. But we are given the volume and the concentration of the sulfuric acid solution that we took for the reaction. And we know how to figure out the number of moles of sulfuric acid present in this solution. So, first figure out the number of moles of sulfuric acid present in the solution taken. How do you get it? The number of moles of sulfuric acid is equal to the product of the molarity of the solution and the volume of the solution in liters. Molarity is 0.200 mole per liter multiplied with volume in liters is 30.0 times 10 to the power of minus 3 liters. This is the amount of sulfuric acid or the number of moles of sulfuric acid present in the solution of sulfuric acid taken. Now, from the number of moles of sulfuric acid taken for the reaction in the form of this solution, can we calculate the number of moles of sodium hydroxide required to react with it? Yes, we have this relationship, right? So, if 1 mole of sulfuric acid requires 2 moles of sodium hydroxide, these many moles of sulfuric acid requires how many moles of sodium hydroxide? So, the number of moles of sodium hydroxide required is this multiplied with 2 over 1, right? So, 0.200 multiplied with 30 multiplied with 10 to the power of minus 3 mole multiplied with 2 over 1, or to be precise 2 mole over 1 mole, these two get cancelled. So, this is the number of moles of sodium hydroxide required to react with the number of moles of sulfuric acid present in 30 milliliters of 0.2 molar aqueous solution of sulfuric acid. But here the reaction is not taking place between pure sodium hydroxide and sulfuric acid. Here it is taking place between an aqueous solution of sodium hydroxide and sulfuric acid, and we are given the molarity of the sodium hydroxide solution taken. So, from the molarity of the solution and the number of moles of sodium hydroxide required to react with the sulfuric acid taken, we have to calculate the volume of the solution of sodium hydroxide to be taken. So, you have to figure out the volume of sodium hydroxide solution that has this molarity that provides these many moles of sodium hydroxide. How do you do that? Molarity is the ratio between amount of substance of solute and the volume of the solution in liters. Now, to get the volume of the solution in liters, you have to divide amount of substance with its molarity. You know the number of moles of sodium hydroxide. It is 0.200 times 30 times 10 to the power of minus 3 mole over the molarity is 0.120 mole per liter. These two get cancelled. Liter inverse goes into the numerator, becomes liter, and simplify the rest of the expression to get the volume of the sodium hydroxide solution needed in liters, and you multiply that with 10 to the power of 3 to get its volume in milliliters. Look at another example. This question says nickel sulfate reacts with sodium phosphate to produce a green precipitate of nickel phosphate and a solution of sodium sulfate. Obviously, this reaction is taking place between aqueous solutions of nickel sulfate and sodium phosphate. Calculate the volume of 0.430 molar nickel sulfate that will completely react with 56 ml of 0.210 molar sodium phosphate. Now, from these stoichiometric coefficients, we understand that 2 mole of sodium phosphate reacts completely with 3 mole of nickel sulfate. That is what these stoichiometric coefficients mean. Now, how many moles of sodium phosphate did we take? That is not given in the question. But we are given the volume and the concentration of the sodium phosphate solution taken. From that data, we have to calculate the number of moles of sodium phosphate present in that solution, or the amount of substance of sodium phosphate present in that solution. How do you get that? It is simply the product of the molarity of the solution and the volume of the solution in liters. Molarity is 0.210 mole per liter multiplied with volume of the solution taken in liters is 56.0 times 10 to the power of minus 3. So we have these many moles of sodium phosphate in the solution of sodium phosphate that we took. Now, can we calculate the number of moles of nickel sulfate required to react with these many moles of sodium phosphate? Of course, we can do that by using this relationship. So, if 2 moles of sodium phosphate reacts completely with 3 moles of nickel sulfate, then these many moles of sodium phosphate react with how many moles of nickel sulfate? So, number of moles of nickel sulfate is equal to this whole thing multiplied with 3 over 2, right? So, that would be 0.210 multiplied with 56.0 multiplied with 10 to the power of minus 3 mole multiplied with 3 mole over 2 mole. So, this is the number of moles of nickel sulfate needed to react completely with 56 ml of sodium phosphate that has this concentration. But the reaction is not taking place between pure nickel sulfate and sodium phosphate. It is taking place between their aqueous solutions. So here we took an aqueous solution of nickel sulfate with this concentration. So now we have to calculate the volume of nickel sulfate solution that has this concentration and that provides these many moles of nickel sulfate. How do you do that? Molarity is the ratio between the number of moles of solute or the amount of substance of solute and the volume of the solution in liters. If you want to find out the volume of the solution needed in liters, divide the amount of substance or number of moles with its molarity, right? The number of moles of nickel sulfate is here. It is 0.210 times 56.0 times 10 to the power of minus 3 times 3 over 2 mole over the molarity of the solution is 0.430. 0.430 mole per liter. Cancel these two. Liter inverse goes into the numerator and becomes liter. Simplify this to get the volume of the nickel sulfate solution needed for this reaction in liters. And if you want it in milliliters, multiply that with 10 to the power of 3. Now what do we have next? Calculate the mass of copper sulfide that will be precipitated by bubbling H2S gas through 150 ml of 0.4 molar copper sulfate solution. And here is the balanced chemical equation for that reaction. Here the reaction is taking place between hydrogen sulfide gas and an aqueous solution of copper sulfate solution, and during this reaction copper sulfide is getting precipitated, leaving behind an aqueous solution of sulfuric acid. How do we answer this question? See, obviously to answer this question we have to look for a relationship between the reactant copper sulfate and the product copper sulfide. And the stoichiometric coefficients of both are 1s. That means 1 mole of copper sulfate produces 1 mole of copper sulfide. But here the reaction is not between solid copper sulfate and H2S. Here the reaction is taking place between an aqueous solution of copper sulfate and H2S. So from the volume and the concentration of the solution taken, we have to first calculate the number of moles of copper sulfate present in the solution taken. You get that by multiplying molarity with the volume of the solution in liters. The molarity is given as 0.400 mole per liter multiplied with volume in liters is 150 times 10 to the power of minus 3 liters. So in the solution of copper sulfate taken, we have so many moles of copper sulfate. See, if you had 1 mole of copper sulfate, you would have got 1 mole of copper sulfide. If you have so many moles of copper sulfate, you will get the same number of moles of copper sulfide also. So this is also equal to the number of moles of copper sulfide. So you already figured out the number of moles of copper sulfide. Then how do you get the mass of copper sulfide? You have to multiply the number of moles of copper sulfide with the molar mass of that compound. The number of moles is 0.400 times 150 times 10 to the power of minus 3 mole. And what is the molar mass of copper sulfide? The relative atomic mass of copper is 63.54 approximately, and that of sulfur is 32, so it would be 95.54. So the molar mass of copper sulfide is 95.54. That is relative formula mass of copper sulfide expressed in gram per mole. These two get cancelled and you will get the mass of the copper sulfide in grams. So this is the mass of copper sulfide produced during this reaction. And the next question says, calculate the molarity of water if its density is 1000 kilogram per meter cube. This question seems to have appeared in a previous IIT JEE examination. But I totally failed to understand the idea behind this question. See, by definition, molarity denoted by capital M is the ratio between the amount of substance of solute or the number of moles of solute and the volume of the solution in liters, or this tells the amount of substance or the number of moles of solute per 1 liter of the solution. Now here we are talking about water, that is pure water. In pure water, what is the solute and what is the solvent and where is the solution? Molarity is defined for a solution, and a solution is a homogeneous mixture of two or more things. What are those two or more things in pure water? See, how are we supposed to answer such a question? Should we imagine that pure water is actually a solution of some solute in pure water, in which the amount of solute is 0, that is NB is equal to 0, and say because NB is equal to 0, the molarity of pure water is 0 mole per liter? Does this make sense? Or for the purpose of answering this question, should we change the definition of molarity altogether? Should we simply say it is the ratio between number of moles and volume in liters, and don't care for the fact that it is actually the number of moles of solute, and what we have in the denominator here is the volume of the solution? Should we simply drop these words altogether from the definition of molarity and reduce it to a ratio between number of moles and volume? Should we totally remove the differentiation between solute, solvent and solution and say that pure water itself is the solute, pure water itself is the solvent, and pure water itself is the solution? One substance plays all the roles? And say because we are given the density of water, we can calculate the mass of 1 liter of water, that will be 1000 grams, and the molar mass of water is 18 gram per mole approximately. So the number of moles of water is given mass, or the mass of 1 liter of water over 18 gram per mole, and I think upon simplification you will get this value as 55.55 or something. So you say 1 liter of water has 55.55 moles of water, so the molarity of pure water is 55.55 mole per liter. Does this make any sense? Are you saying that there is 55.55 moles of water in 1 liter of water, where the solute is water, the solvent is water, and the solution is water? It does not make sense to me. See, molarity is a concentration term that tells the concentration of solute in a given volume of the solution. It is defined for solutions, and solutions are homogeneous mixtures of two or more substances. Pure substances are not solutions. They are not mixtures. Therefore, we cannot apply molarity to a pure substance. So this question does not make any sense to me, and I really doubt if this question really appeared in a previous JEE examination. Now let us work out a few examples on conversion of concentration terms. Earlier I told you that we can easily convert percentage by mass into molality and mole fraction because these three concentration terms either directly or indirectly depend only on the mass of the solute, the mass of the solvent, and the mass of the solution. And this question says, Clorox is a household bleach that is 7.4% aqueous solution of sodium hypochlorite NaOCl. Assuming there is no other substance in the solution, find the molality of the solution and mole fraction of each component in the solution. By the way, what are the components present in this solution? Obviously, it is an aqueous solution of sodium hypochlorite. That is, it is sodium hypochlorite that is dispersed in water because it is an aqueous solution. So, the substance that is dispersed or dissolved is called the solute. So, here the solute is NaOCl. And it is dispersed in water, right? So the solvent is water. And it is given that the percentage by mass of this solution is 7.4. By the way, in addition to these two substances, Clorox contains some other substances also that are added to increase the stability of the solution. But for the purpose of this question, we are asked to assume that there is no other substance in the solution. So assume that this solution contains only one solute dissolved in water. Now we have to first calculate the molality of the solution, that is small m. How do we do this? Molality is nothing but the ratio between the number of moles of solute and the mass of the solvent in kilograms, right? So to know the molality of the solution, you need to figure out these two. How do we do that? Given the percentage by mass. Remember, the molality of a given solution is a constant. That is, this ratio is always the same irrespective of the amount of solution you have taken. Pay attention to this. Whether you take 100 grams of the solution or 1 gram of the solution or 1000 grams of the solution, if it is the same solution, then they will all have the same molality. This ratio is going to be the same. Of course, the number of moles of solute will change with the amount of solution you have taken. Also, the mass of the solvent changes with the amount of solution you have taken. But the ratio always remains the same for a given solution. Because the concentration of a solution does not change with the amount of solution taken, for this calculation, I will take 100 grams of the solution. Because I am given percentage by mass, it becomes easier for me. And the percentage by mass is given as 7.4. That means if you take 100 grams of the solution, it contains 7.4 grams of solute, and the solute in this case is sodium hypochlorite. So the mass of the solute in the solution I took is 7.4 grams. Then what is the mass of the solvent? The sum of the mass of the solvent and the mass of the solute is equal to the mass of the solution, and the mass of the solution I took is 100 grams. So Ma plus Mb is equal to 100 grams. Then mass of the solvent Ma is equal to 100 minus mb grams. And the mass of the solute is 7.4 grams. So it will be 100 minus 7.4 grams. So this is the mass of the solvent in grams. But we need the mass of the solvent in kilograms. Because molality is the ratio between amount of substance of solute or the number of moles of solute and the mass of the solvent in kilograms. So the mass of solvent in kilograms would be 100 minus 7.4 times 10 to the power of minus 3 kilograms, because you know 1 gram is equal to 10 to the power of minus 3 kilograms. So we already figured out the mass of the solvent in kilograms. Now we have to figure out the amount of substance or the number of moles of solute, that is NB. How do you find out the value of NB given the mass of the solute? You have to divide the given mass with its molar mass, right? What is the molar mass of sodium hypochlorite? Is it 23 plus 16 plus 35.5 approximately? So 6 plus 5, 11 plus 3, 14, 1, 7, 74.5. So the molar mass of sodium hypochlorite is 74.5 gram per mole. So NB is equal to MB over the molar mass of sodium hypochlorite. The mass of sodium hypochlorite is 7.4 grams and the molar mass is 74.5 gram per mole. So cancel these two and simplify this to get the value of NB. Then molality is equal to NB over the mass of the solvent in kilograms. So you have the value of NB here, you have the value of MA here. Substitute them in this expression, then it would be 7.4 over 74.5 mole. Mole inverse becomes mole when it comes to the numerator over 100 minus 7.4 times 10 to the power of minus 3 kilograms. So you will get the molality in mole per kilogram. Now what about mole fraction of each component in the solution, that is mole fraction of solute and the solvent? See, because solution is a homogeneous mixture, the mole fraction of a component in a solution is also independent of the amount of solution taken. It must be same whether you take 100 grams or 50 grams or 1 gram or 0.5 gram of the solution. So let us go with 100 grams of the solution again. So the mass of the solute is 7.4 grams and the mass of the solvent is 100 minus 7.4 grams. Now to get the mole fraction of solute, you need to know the number of moles of solute and the total number of moles present in the solution taken. And the total number of moles is nothing but the sum of the number of moles of each component in the solution. So the mole fraction of solute is the ratio between the number of moles of solute and the total number of moles present in the solution. How do you get the number of moles of solute? You already figured that out here, right? So it is 7.4 over 74.5 mole. That is the number of moles of solute present in 100 grams of the solution. Remember, we took 100 grams of the solution. Then how do you get the number of moles of solvent? Na is again equal to the mass of the solvent over its molar mass. Molar mass of water is approximately 18 gram per mole. Remember, here the solvent is water. So cancel these two and simplify this to get the number of moles of solvent. You know the value of NB, you know the value of Na. Substitute them in this expression to get the mole fraction of solute. Then to get the mole fraction of solvent, you know that XA plus XB is equal to 1. So XA is equal to 1 minus XB. Sum of the mole fractions of all the components in a solution must be equal to 1. Here there are only two components, so XA plus XB must be equal to 1. Or if you want to calculate XA from this expression, that is Na over Na plus Nb, you can do that. You will get the same answer. So we are able to easily convert percentage by mass into molality and mole fraction. Now let us look at another example. Calculate the following for a solution of methanol, that is methyl alcohol. In ethanol, see here the solvent is ethyl alcohol, not water. This is not an aqueous solution, and we are given the molality of the solution. Notice this small m here. Small m represents molality. Then we are asked to calculate the mole fraction of methanol and ethanol. Methanol is the solute here and ethanol is the solvent. Also calculate percentage by mass of the solution. Can you give it a shot? Now what is the meaning of 0.250 molal solution? It means in 1 kg of the solvent, pay attention to this, 1 kg of the solvent, not solution. In 1 kg of the solvent, there is 0.250 moles of solute. Here what is the solute? Methanol, that is CH3OH. And what is the solvent here? Ethanol, C2H5OH. This is the meaning of 0.250 molal solution. Now assume that the solution that you took has 1 kg of solvent. That would be convenient for our calculations. So consider 1 kilogram of the solvent. Then the mass of the solvent is 1 kilogram, right? Ma is 1 kilogram. And you know the number of moles of solute present in that solvent. Nb is 0.250 mole. Then how do you figure out the mass of the solute given the number of moles or amount of substance? You have to multiply it with its molar mass, right? The molar mass of CH3OH. The number of moles is 0.250 mole multiplied with what is the molar mass of CH3OH? 12 plus 16 plus 4, right? 10 plus 2, 12, 32. So it is approximately 32 gram per mole. So here is the mass of methyl alcohol or the solute in grams. And here we have the mass of the solvent, that is ethyl alcohol, in kilograms, and in grams it would be 1.0 times 10 to the power of 3 grams. Now what do we have to calculate first? Mole fraction of methanol and ethanol. Now the mole fraction of solute, that is methyl alcohol, is the number of moles of solute over the total number of moles present in the solution. You already know the number of moles of solute in the solution you have taken, that is 0.250 mole. Now because you know the mass of the solvent, that is ethyl alcohol, you can determine the number of moles of solvent, that is mass of the solvent over the molar mass of the solvent. In this case it is ethyl alcohol. What is the molar mass of ethyl alcohol? 24 plus 6 plus 16, right? 12 plus 4, 6, 1. Is it 46? So it is approximately 46 gram per mole. And what is the mass of the solvent or ethyl alcohol? 1.0 into 10 to the power of 3 grams. So this will give you the number of moles of solvent, and here you already have the number of moles of solute. So the mole fraction of solute would be 0.250 mole over MA is 1.0 into 10 to the power of 3 over 46 mole plus 0.250 mole. They get cancelled, and simplify this to get mole fraction of methyl alcohol. Remember, it is a dimensionless number. Then you know how to calculate the mole fraction of ethyl alcohol. XA is 1 minus XP. This solution has only two components, and the sum of the mole fractions of all components must be equal to 1 for any solution. Then what about percentage by mass of the solution? Simple. You know the mass of the solute, you know the mass of the solvent. So percentage by mass is equal to mass of the solute over the mass of the solution, that is MA plus MB. You know the value of MB, that is 0.250 into 10 to the into 32 grams over MA is 1.0 into 10 to the power of 3 grams plus again this 0.250 into 32 grams. They get cancelled, and simplify this to get again percentage by mass. And this is also a dimensionless number. So that is how you can convert these concentration terms. Now the next question says calculate the molarity, that is molar concentration of 1.84 molal, small m means molality, aqueous solution of urea. See, here we are given the molality of the solution, and we are asked to calculate the molarity of the solution. We are given small m and we are asked to calculate capital M. How do we do that? The molality of the solution is 1.84. That means if you take 1 kilogram of the solvent, by the way, what is the solvent here? We are talking about an aqueous solution. That means the solvent here is water. So in 1 kilogram of water, there is 1.84 mole of solute. And what is the solute here? Urea, right? It is urea that is dispersed or dissolved in water. The substance that is dissolved is the solute, and the substance that is dissolving is the solvent. So urea is the solute and water is the solvent. Then can you figure out the mass of urea dissolved in 1 kilogram of water? You can do that, right? Given the amount of substance or the number of moles of urea. The mass of urea or the mass of solute is number of moles of solute multiplied with the molar mass of the solute. Here the solute is urea, and the molecular formula of urea is NH2 twice CO. Then what is its molar mass? Is it 14 plus 2, 16 times 2 is 32 plus 12 plus 16 again, right? So is it 60? Yeah, it is approximately 60 gram per mole. So NB is 1.84 mole multiplied with 60 gram per mole. Cancel these two and simplify this to get the mass of urea or the mass of solute in grams. So this is the mass of solute or urea dissolved in 1 kilogram of solvent, that is water. Then what will be the mass of the solution that contains 1 kilogram of water and 1.84 moles of urea? It is nothing but the sum of the mass of the solvent and the mass of the solute, right? Ma is 1 kilogram and in grams it would be 1.0 into 10 to the power of 3 plus it has 1.84 moles of urea or so many grams of urea, that is 1.84 times 60 grams of urea. So this is the total mass of the solution that contains 1 kilogram of the solvent and 1.84 moles of urea. Or in other words, 1.84 mole of urea is present in so many grams of the solution. So you know the amount of substance of solute or the number of moles of solute, that is urea, and the mass of the solution, that is this. Now how do you calculate the molarity of a solution denoted by capital M? It is the number of moles of solute or the amount of substance of solute over the volume of the solution in liters. Wait a minute. What we have here is the mass of the solution. But to calculate molarity, we need the volume of the solution. Then how do we answer this question? How do you figure out the volume of the solution from the mass of the solution? For that, you need to know the density of the solution, right? Density of a substance is the ratio between the mass and its volume, right? So this is the expression for the density of the solution. I know the mass of the solution, so to figure out the volume of the solution, I need to know the density of the solution. So I cannot answer this question with this information alone. To answer this question, I must also be given the density of the solution. Pay attention to that. Not the density of the solvent or the solute. We must be given the density of the solution as well. Say the density of this solution is 1.028 gram per milliliter. Then, because we know the mass of the solution and the density of the solution, we can calculate the volume of the solution. So what will be the volume of the solution? Mass of the solution is this much in grams. So it is 1.0 into 10 to the power of 3 plus 1.84 into 60 grams over its density is given as 1.028 gram per milliliter. Cancel these two. Milliliter inverse goes into the numerator and becomes milliliter. So this will be the volume of the solution in milliliters. But here we need the volume of the solution in liters. So convert the volume into liters by multiplying it with 10 to the power of minus 3. So there you have the volume of the solution in liters. And you know the number of moles of solute or the amount of substance of solute. It is 1.84. So it is 1.84 mole over this thing, right? 1.028 comes into the numerator. So it is 1.028 over 1.0 into 10 to the power of 3 plus 1.84 into 60 liters. Don't forget this 10 to the power of minus 3 as well. So simplify this to get the molarity of the solution in mole per liter. So it is going to be a little tricky to convert molality into molarity. Also, you must know the density of the solution to do this. So go through this workout one more time to understand it. Now in the next question, let us do the opposite. Let us calculate the molality of the solution given the molarity of the solution. An aqueous solution of sodium carbonate has a concentration of 0.820 m. Capital M is molarity. At this temperature, the density of the solution is so and so. Calculate its molality. Now, what do we mean by this molarity? If you take 1 liter of the solution, then it contains 0.820 moles of solute. Here what is the solute? Sodium carbonate. Sodium carbonate is the substance that is dispersed or dissolved in the solvent, and the solvent here is water because it is an aqueous solution. So in 1 liter of the solution we have so many moles of sodium carbonate. So for our calculations, it would be convenient if you take or consider 1 liter of the solution. So we are doing these calculations on 1 liter of the solution. 1 liter of the solution has so many moles of sodium carbonate. So NB, that is the amount of substance of solute, is so much. Then can you calculate the mass of sodium carbonate or the mass of solute? Simple. Amount of substance multiplied with its molar mass. The molar mass of sodium carbonate is approximately 106 gram per mole. So this is the mass of the solute or sodium carbonate present in 1 liter of the solution. Then what is the mass of 1 liter of the solution? Its density is given, right? So you have to multiply the density of the solution with the volume of the solution. Volume of the solution we considered is 1 liter, or in milliliters it is 1.0 into 10 to the power of 3. And this is the density. When you multiply these two, you will get the mass of the solution. This is the mass of 1 liter of the solution. Mass of the solution is nothing but sum of the masses of the solvent and the solute, Ma plus Mb. Then what will be the mass of the solvent? By the way, here the solvent is water, right? So the mass of water is mass of the solution minus Mb. This is the mass of the solvent, that is water in this case in grams. To convert it into kilograms, multiply it with 10 to the power of minus 3. So in 1 liter of the solution, there is 0.82 moles of the solute and so many kilograms of the solvent. So you know Nb and Ma present in 1 liter of the solution. Substitute these values in this expression and simplify to get the molality of the solution in mole per kilogram. Finally, let us look at the expressions for molality and molarity. Molality, that is small m, is the ratio between amount of substance or the number of moles of solute and the mass of the solvent in kilograms. Molarity is the ratio between amount of substance or the number of moles of solute and the volume of the solution in liters. Now let us consider a very dilute solution. A very dilute solution is prepared by dissolving a very small amount of solute in a large amount of solvent. So in such a solution, the amount of solute is very, very small compared to the amount of the solvent or the amount of the solution formed. Because a very dilute solution is prepared by adding or dissolving a very small amount of solute in a large amount of solvent, the addition of such a small amount of solute does not significantly change the volume of the solvent. Then what can we say about the volume of the solution? Because the addition of such a small amount of solute is not significantly changing the volume of the solvent in which it is dissolved, the volume of the solution formed is approximately equal to the volume of the solvent, right? Because the addition of such a small amount of solute is not changing significantly the volume of the solvent. So therefore, the volume of the solution formed is almost equal to the volume of the solvent in which this small amount of solute is dissolved. Therefore, we can say that the volume of the solution is approximately equal to the volume of the solvent. Now, in that case, can I replace volume of solution in this expression with volume of solvent for a very dilute solution? Yes. So, for a very dilute solution, I can say molarity is equal to the ratio between amount of substance of solute and the volume of the solvent in liters. Now, if the solvent is water, it is called an aqueous solution, right? And the density of water under normal conditions is 1 kilogram per liter. What does this mean? This means 1 liter of water under normal conditions weighs 1 kilogram. So, the volume of water expressed in liters, that is 1.0, is numerically equal to the mass of water expressed in kilograms, that is also 1.0, right? These two have the same value. So, under normal conditions, the volume of water expressed in liters is numerically equal to the mass of water expressed in kilograms. I know they are two different physical quantities, but I am saying that they are numerically equal. I am not saying that they are the same physical quantity. So, because the density of water under normal conditions is 1 kilogram per liter, the volume of water expressed in liters is numerically equal to the mass of water expressed in kilograms. Now, if you compare these two expressions for a very dilute aqueous solution, obviously we have the same value in the numerator in both the expressions. Their numerators are the same, and their denominators are also approximately equal for a very dilute aqueous solution. That is because for a very dilute solution, the volume of the solution is approximately equal to the volume of the solvent, and under normal conditions, the density of water is 1 kilogram per liter. So, the volume of water in liters is approximately equal to the mass of water in kilograms. So, their denominators are also approximately equal. Therefore, these two ratios must be approximately equal for a very dilute aqueous solution. So for a very dilute aqueous solution, the molality of the solution is approximately equal to its molarity. This holds good only for very dilute aqueous solutions. It may not hold good for non-aqueous solutions even if they are dilute, because the density of those solvents will not be 1 kilogram per liter under normal conditions. So only for very dilute aqueous solutions, sometimes you have to use this approximation for some calculations.